Hello, my name is Arp Mishra, and this is problem number 1 of my final project. And for this problem, basically, I said you are building a half sphere igloo, and I give you the appropriate temperatures at the inside that you want of the igloo and the outside, and then the different convective heat transfer coefficients and the dimensions. And what I want to find out is the heat transfer through the ice. And I also want a resistance network drawn in this. So we can assume that it's steady 1D heat transfer through the ice, constant thermal properties, and heat transfer is occurring via conduction and conduction only. Property I needed to look up was the thermal conductivity of ice. So then for the solution, drew a resistance network right here, and then did the appropriate resistance diagram for it. Then we need to figure out the area of the half sphere, both at the inner and the outer radii, and then we could figure out our convective at the inner, which was this, and then we could figure out the resistance of the ice, which was this correlation that was off of our handouts or in our equation sheet, and then our convective of the outer. And then basically, in order to solve this problem, we have to do just sum all of them up, and we get a total resistance here, and then the heat transfer of the ice is just equal to the temperature at the inside minus temperature at the outside over the total resistance, and we basically just plugged all that in and got an answer here. And this covers learning outcomes 1B, 3, and 5C. For problem 2, I say you decide to go into the wilderness with the nylon sleeping bag, and you find a cave and you start a fire, and the fire gives off a heat flux of this value here. I give you the heat transfer coefficient at the outer surface of the sleeping bag, the temperature at the outer surface of the sleeping bag, and I said you could assume the sleeping bag to be like a cylinder, so those are inner outer radiuses. Then we can find, I asked you to find the temperature of the insides of the sleeping bag, and we start from energy balance. And so we can assume steady 1D radial heat conduction, constant thermal properties, no heat gen from the person inside the sleeping bag, and outer surface of the sleeping bag is subject to convection only. Properties I had to look up was thermal conductivity of a nylon sleeping bag. So for the solution, we start with the energy balance. And so we cancel out E gen because there's no heat generated, and the energy with the respect to time because it's at steady state. So then we just replace that with Q. And then we have Q at the inner radius minus Q at the outer radius equals 0. Divide both sides by negative delta R to match definition of derivative. Then we take the limit of delta R as it approaches 0. Then we get this value here. And then from Fourier's law, we know that dq dr is equal to this nice value here. Just plug it in. And then for the area, we know that it's a cylinder, so it's 2 pi RL. Then the 2 pi RL and K are all constants, so we can pull them out and cancel them away. We get this nice equation here. Then we use the boundary conditions of boundary condition 1, where it's a finite heat flux, boundary condition 2, which is constant surface temperature. And so we integrate applied boundary condition 1, get this, integrate again, and we get this value here after applying boundary condition 2. Then you just plug in the respective values, and we want to solve for the temperature at R1, which is the inner radius, and we get this value here. And this covers learning outcomes 2A and 2B. Then for problem 3, we want to cool hot oil with water in a shell and tube heat exchanger. And so since we know it's a shell and tube heat exchanger, we know the friction correction factor is 1. And so I give you all the values. I also give you the heat transfer coefficient for the oil, and I give you the flow rate of the water, the different temperatures in and out of both the hot and cold stream. So we need to find the overall heat transfer coefficient and the area of the tube by the log mean temperature method. And so we can assume thermal resistance of inner tube is negligible, oil and water fully developed, oil and water properties are constant, and water flow in the inner tubes is internal flow in this case. So water properties at 45 degrees, which is T film of the 2 cold streams in and out, the average of them. So then I have all these properties here. Then for a solution, we have oil already, so we need to figure out what water's heat transfer coefficient is. And so in order to do that, we solve for the velocity that from the given values, and then we can get Reynolds number, which we can then determine that the flow is turbulent. Then using the appropriate correlation for internal flow and Nusselt number, we can figure out what the value of the Nusselt number is. Then we can just plug that in and rearrange and then solve for the heat transfer coefficient for the water. And then for the overall heat transfer coefficient, it's this correlation here where 1 over U equals 1 over the other heat transfer coefficients summed together. We can figure out, then we get the total answer here. Then in order to figure out the area of the tube, we have to figure out what the total value of Q is. Then we have to figure out delta T log mean, which we get there. And then just rearranging and solving for the area, we get this value here. And this covers learning outcomes 7A and 8A. For problem 4, I said that there's a log line on its side in the middle of the forest, and it can be approximated to be like a long, like a cylinder with a diameter of 0.5 meters and a length of 1.5 meters. And then I give the ambient temperature of the forest, the surface temperature of the log, and if it's windy, what the speed of the wind is. So then for part A, I asked to find the heat transfer from the wind to the log if it's windy, so external forced, and find heat transfer from the wind to the log if it's not windy, so natural convection. So we can assume steady state operating conditions, no radiation, and constant air properties. So for the air properties, we use the T film. So that's what I did here. And then I just pulled all the values. And then beta is equal to 1 over the temperature. So that's what I got there. So for part A, the solution, we figure out Reynolds number, which is here. And then from that, we plugged it into the Nusselt number for flow over a cylinder, plug everything in, got a value here. Then I was able to solve for the heat transfer coefficient with the Nusselt number, and I got a value here. And then determined what the overall heat transfer was by plugging in, using this equation here and just plugging in what the area was, and I got a value here. And then for the natural convection, we first figure out the Raleigh's number and then solve for that. And so since we know that Rayleigh is less than 10 to the 12th, we can use the correlation for natural flow over a cylinder. So that's what I did here, got Nusselt number for that, and then just rearranged and solved for the heat transfer coefficient again, and then figured out the overall heat transfer from the wind to the log if it's not windy. And this covers learning outcomes 7B and C. Okay, for problem 5, we are getting ready to boil some water in a chemically etched stainless steel pan at a pressure of 1 atm, which is 101.33 kPa. And the inner surface of the bottom of the pan is supposed to be maintained at 110 degrees Celsius, and the diameter of that bottom of the pan is 25 centimeters. So we are asked to find the rate of the heat transfer to the water. And in order to be able to do that, you're going to have to find Q nucleate. So assuming that it's a steady state operation, additional heat losses from the heater and the pan are also negligible. So we need to figure out what the water properties are at Tsat. And Tsat in this case would be what it is at 101.33 kPa. And so we figured out all the values for that. And additionally, for Q nucleate, we need to figure out what sigma is. And then we need to figure out what CSF is and NR, both from these tables. And in order to be able to use Q nucleate in this solution, we have to make sure that delta T, which is change in temperature of the surface and between the surface and the saturation temperature, we need to make sure it's between 5 degrees Celsius and 30 degrees Celsius, which it is. Then you just plug in all the values for Q nucleate, and then we get an answer here. And then to figure out what the heat transfer is from to the water, we just have to multiply times the area, which is just the bottom of the pan, and we get this value here. And this covers learning outcome 7D. Okay, for my final problem, we're trying to determine what the area of a membrane would be to require an achieved separation. So we have a membrane with the film deposited on the inside wall of a porous stainless steel tube, and it's being used to remove CO2 from natural gas, which is CH4 and CO2. And so the gas stream from the wellhead contains 0.3 CO2 and the balance CH4. And we know the feed flow, the sweep flow rate. We know the pressure at the feed and the retentate are the same, and the pressure at the sweep and the permeate are the same. And we know the CO2 permeance, and we want us to achieve a 75% removal of CO2. So like I said earlier, the find is the area of the membrane required to achieve desired separation. So in order to do that, we will also need to find the flow rates of each component and the driving force of CO2 permeation through the membrane. So we can assume that there's a driving force pushing for a certain outcome and that this is perfectly selective for CO2. Here's the drawing. And so we need to figure out the flow rates. So F is feed, P is permeate, R is retentate, and S is sweep. And so these are just simple material balances, and we just can solve for them. And then we figure out what the driving force for CO2 is with this equation here, which is analogous to the change in temperature log mean derivation. So we just figure out the different values right here, plug them in, and then we can get that the change in pressure of CO2 is equal to 99.82 kPa. And then from that, we have this correlation, which relates to the permeance of CO2. We rearrange and solve, and we get this value. And then the area is just the moles of CO2 in the permeate divided by this value, and we get this answer here. And this covers learning outcome 8B.